In this video, I'm going to work out some answers, some solutions to the homework problems in section 4.3. 4.3 deals with derivatives and the shapes of curves. Specifically, it deals with the first derivative test, the test for concavity, the increasing, decreasing test. The typical question asks us to determine the intervals upon which the function is increasing, decreasing, find local mins, local maxes. On top of that, they also often ask us to determine when a function is concave up and concave down, and to find any related inflection points. So this is going to be section 4.3, homework solutions. I'm not going to do some of the simpler problems, the polynomial-oriented questions. Those are often answered in the, well, we have examples in our book that deal with those. So I'm going to skip down and start with problem 31. I may put another video together that deals with maybe, something like problem 7 or problem, something simpler. But right here, I just want to start with problem 31 because why? Well, problem 31 is trig, and often the trig questions are the questions that cause us the most trouble. So we have f of theta equals 2 cosine theta plus cosine squared theta. And because Mr. Stewart, who is our author, has given us a gift here, we have a restriction on our domain. Theta is bounded below by 0 and above by 2 pi. Below by 0, above by 2 pi. So how do we begin? Well, we begin by realizing we're going to have to run a sign test for the first derivative, and we're going to need to run a sign test for the second derivative. And so the first step on any of these problems is to calculate our derivatives. So if we do that, we find the first derivative. The derivative of cosine is negative sine, so this is going to be minus 2 sine theta. Here, we're going to take the derivative of cosine squared, so we're going to use the chain rule. That's going to be plus 2 cosine of theta times the derivative of the inside function, cosine. The derivative of cosine is negative sine theta. So if we simplify this, right, factor out a negative 2 sine theta here, we have a negative 2 sine theta. What's left here is a 1. What's left here is plus cosine of theta. All right? Now, to find the second derivative, we could use the product rule. I'll get us started on that. I probably won't calculate the entire second derivative. I worked it out ahead of time, and I'll probably just rely on that answer, but I will at least get started here. The second derivative, of course, is going to be fg, right, product rule. So it's the derivative of f, so we have negative 2, that's our constant, times the derivative of sine, which is cosine of theta, times g, so that's 1 plus cosine theta. Now plus f, right, which turns out to be negative 2 sine theta, times the derivative of g. The derivative of g, the derivative of 1 plus cosine theta, is going to be minus sine theta. Now what can we do here? Well, if we expand this, right, if we expand this, multiply it out, we have minus 2 cosine of theta minus 2 cosine squared theta. Over here, we have minus 2 sine squared theta. Oh, I'm sorry, that would be plus, right? Negative times negative. Sine squared theta. So from here, we can rewrite this sine squared as 1 minus cosine squared. The reason for that is we have a cosine squared and a cosine. And remember, we want to be able to factor these derivatives. The sign test is easiest if we have factorable derivatives and second derivatives. So from here, I'm just going to put a squiggly line and tell you if you would have, right? If you would have replaced this with cosines, 1 minus cosine squared, distributed and factored, you would end up with a second derivative that is minus 2 times 2 cosine theta minus 1 times cosine theta plus 1. All right? So that's our first derivative, and that's our second derivative. So where do we go from here? Well, from here, right, from here, we have our two derivatives. Let's copy those two derivatives up here, just to get them out of the way. F prime of theta is going to be negative 2 sine theta times 1 plus cosine theta, right? And then F double prime of theta is going to be negative 2 times a quantity, 2 cosine theta minus 1 times cosine of theta plus 1. Okay? So we'll write our derivatives up there. The reason I'm doing that is I'm going to go ahead and erase this to free up some space. I'm going to erase this work here just to free up some space, because the problems, the way they're laid out when they ask us where is this increasing, where is this decreasing, find the intervals of concavity, where is it concave up, where is it concave down, find the local mins, find the inflection points. That requires a lot of work, and so I want to free up a lot of space. And on problem 31, the reason I skipped down to 31 is it has an added extra step where they want us to draw the graph of the function without using a calculator, right? So let me just slide this down a little bit here so we can get this onto the screen. There we go. So where do we go from here? Well, we're going to use our first derivative. We're going to take our first derivative and we're going to try to find the critical numbers. So we want to find the critical numbers for f prime of x, right? That's what we want to do. So how will we do that? Well, we're going to take f prime of x and we're going to set it equal to 0. So that gives us, or in this case, f prime of theta. So we have f prime of theta, which equals theta equals negative 2 sine theta times 1 plus cosine of theta. Now, we know how to find the critical numbers. We start with when does the derivative equal 0, right? That's our first step. Negative 2 is not 0. That's a factor, but it's not 0. So we have sine theta equals 0. Or, right, we have 1 plus cosine of theta equals 0. Now, when does sine theta equal 0? Well, remember now, we're restricted on our domain from 0 to 2 pi. So if we draw a quick graph of sine, we can see that sine theta equals 0. That gives us theta equals 0, right? Theta equals pi, and theta equals 2 pi is our possible critical values. What about cosine theta equals 1? Well, that's not cosine theta equals 1, is it? That's cosine of theta equals negative 1. If we draw a quick graph of cosine looks like this. That's going to give us theta equals pi, right? Theta equals pi. So those are our critical numbers. So now we're going to conduct our sign test. Now, the sign test, remember, we just draw our number line. Now, because we're on a closed interval, 0 to 2 pi are endpoints, it turns out. Our only other critical number is pi. Our factors are negative 2, sine theta, and cosine theta plus 1. Those are our three factors. Now, it's very important for us to make sure that we take note of one of our factors is a constant. We're not going to plug in test points for that, but it's not just a constant, it's -2, which means that's going to be negative and that's going to be negative for any test point because it's a negative constant. If we would not have remembered to include this, we would have been off down here by a negative sign. In other words, if this would have said negative, it should have really been positive. If this would have said positive, it really should have been negative. So be very careful with your constants. I like to put my constant into my sign test, whether it's positive or negative, just so I get into the habit of including it. Now, what about cosine theta plus 1? Well, if we think, right, if we just think about what cosine theta plus 1 looks like, here's our graph of cosine. Cosine theta plus 1 is this graph shifted up 1. Well, if we shift that graph up 1, that graph is never negative. So cosine theta plus 1 is going to be positive no matter what point we pick in those intervals. One of the nicer things about the trig functions, I know a lot of us don't enjoy them as much as we enjoy the polynomials, but one of the nicer things about the trig functions is the sign test, we normally don't need to pick values here. We can usually get away with just taking a look at our graphs. For example, sine theta. If I look at the graph of sine theta, pi is here, right? This is pi right here. So sine is positive to the left of pi and negative to the right of pi. So sign tests with trig functions often work out a little quicker than sign tests with polynomials because we don't have to plug in points as often. What do we get here? We get negative here, negative, negative, positive. We get positive here. So what do we know? We know f is decreasing on 0 to pi, and f is increasing on pi to 2 pi. Now these are open on the ends because these are zeros of my derivative. Zeros. They're places where my derivative equals 0. Our book specifically says a function is increasing if the derivative is greater than 0, not if the derivative is greater than or equal to 0. So we have to make sure we have open intervals there. What do we know about pi? Well, we know pi, right? If we take a look at this function's decreasing here and then increasing over here. So pi is a local minimum. So we can say f has a local min at x equals pi. The local minimum value is f of pi. All right, so you and I are going to have to calculate f of pi. Now our function's back here. Cosine of pi, cosine's drawn here. Cosine of pi is -1. So this is 2 times -1, so that's going to be -2. We just said cosine of pi is -1. -1 squared is going to be 1, so that's +1, and we end up with a minimum value of -1. So our local minimum value is -1. Now, they asked us, where is our function increasing and decreasing? We've got that. They asked to find the local maximum and minimum values. We have that. What haven't we done? Well, we haven't done concavity yet, right? We haven't addressed concavity. We've done all of our work over here in a nice organized manner, and we addressed the first derivative to talk about mins, maxes, increasing and decreasing. Now we're going to shift gears. We're going to go over here and we're going to find the critical numbers, right? Of f double prime of beta, right? Not x. Now, this is going to look a lot like this. We're going to do exactly the same steps here that we did here. Unfortunately or fortunately for us, we're going to use the second derivative here. It looks like it's a little more complicated, but I don't really think it's going to be too much to handle. We're going to find the critical numbers of the second derivative. We're going to duplicate this work right here on the whiteboard. So what are we going to do? Well, we're going to start with of theta equals 0, right? F double prime of theta equals 0. So what are we going to do? We're going to set this equal to 0. When is this equal to 0? Well, you know, F double prime of theta is equal to 0 when the factors that make up F double prime are 0. So negative 2 is not a 0. So we're going to have 2 cosine of theta minus 1 equals 0. Or we're going to have cosine of theta plus 1 equals 0. Those are going to be our two equations that are going to give us our critical values. This one you and I have already solved, right? We solved that here. We had 1 plus cosine theta equals 0 as a factor of our first derivative as well. And so therefore, we already know what this gives us, right? This gives us theta equals pi. We can put that down right now, save ourselves the work, no use redoing the analysis. What do we end up with over here? We move the 1 over, we divide by 2, we get cosine of theta equals positive 1/2, all right? Now we're going to have to solve that. How are we going to solve that? Well, we're going to go back to our pre-calc and we're going to use our quadrant and reference angle analysis to solve this. Cosine's positive, right? So we'll draw a little graph right here real quick. All students take calculus. And where is cosine positive? Cosine positive 1/2, so cosine's positive in quadrant 1. So we have quadrant 1 and we have quadrant 4. Right? Those are our quadrants. Now we need a reference angle. Remember, cosine is adjacent over hypotenuse. We'll draw ourselves a triangle right here. 1 and 2 are adjacent side or hypotenuse. This, of course, is the square root of 3. This is a rectangle, a triangle that we all know. This is pi over 3. So our reference angle is pi over 3. Now, we have a reference angle of pi over 3 in quadrant 1 and quadrant 4. So if we just use this open space right here, a reference angle of pi over 3 in quadrant 1, a reference angle of pi over 3 in quadrant 4, and we get two new critical values. We get theta equals pi over 3, and we get theta equals 5 pi over 3. Right? Those are our critical values for the second derivative. So we have all of our critical values for the second derivative. So now we remember, we're just duplicating the work over here. So the next step is going to be to conduct the sign test. Now, what does that mean for us? Well, it means we're going to plot all of our critical values. Remember, we're beginning at 0. Our first critical value is pi over 3. Right? So we'll just put that down. Scale doesn't matter. Then we have pi. Then we have 5 pi over 3. And then we have 2 pi. And what are the factors of our second derivative? Well, the factors of our second derivative are, again, we have a negative 2 as a factor, right? We have a negative 2. We have 2 cosine theta minus 1. And we have cosine theta plus 1. Now, 2 of these values we're very comfortable with. This is negative 2. We know in all 4 of these intervals, negative 2 is going to return a value that's negative. It's constant. Cosine theta plus 1, we've analyzed that graph over here. We know that graph is always positive. Now that leaves us 2 cosine theta minus 1. We need to figure out how are we going to analyze 2 cosine theta plus 1. One way we could do that is we could just pick test points and plug them in. Right? We could, and perhaps that's what we should do is just because we haven't practiced test points, let's just grab a test point. What do we know is between 0 and pi over 3? Well, 0 and pi over 3 is right here, so what do we have that's convenient between 0 and pi over 3? We could use pi over 6, we could use pi over 4, right? Both of those are between 0 and pi over 3. Let's use pi over 6 just because we already have the triangle drawn for that here. So if we consider our test point to be pi over 6, we'd have to find cosine of pi over 6. Pi over 6 is here. Cosine is adjacent over hypotenuse. So adjacent would be root 3. Hypotenuse would be 2. So that'd be root of 3 over 2 times 2. That'd be the square root of 3 minus 1. Well, the square root of 3 minus 1 is going to be positive because the square root of 3 is bigger than 1. Now we need a number between pi over 3 and pi. Remember, pi over 3 is here. Pi is way over here. So we could use pi over 2, right? We know cosine of pi over 2 is 0 from right here on this picture. Cosine of pi over 2 is 0. So this is 2 times 0 minus 1. That's going to be negative. We need a number between pi is here, and 5 pi over 3. We could use 3 pi over 2, right? 3 pi over 2 works fine. What do we know about 3 pi over 2? Well, we know 3 pi over 2 is, cosine of 3 pi over 2 is 0, so that's 0 minus 1. That's also going to be negative. Now we need a number between 5 pi over 3 and 2 pi. 5 pi over 3 and 2 pi is here. We could use 11 pi over 6 if we wanted to, right? We're doing cosine. 11 pi over 6 has a reference angle of pi over 6, root 3 over 2. We're in quadrant 4. Quadrant 4 cosine is positive, so we'd have root 3 over 2 times 2, so square root of 3 minus 1. That's going to be positive. And if we do our analysis, here we get a minus, here we get a plus, here we get a plus again, and here we get a minus. Right? There's no rule that says these have to alternate. In fact, sometimes they do and sometimes they don't. We won't know until we do our analysis. So what are we going to conclude here? Well, we're going to conclude that f is concave down on 0 to pi over 3 union 5 pi over 3 to 2 pi. And f is concave up on pi over 3 to pi union pi to 5 pi over 3. Now, here you're going to have to be a little careful. You're going to have to look at your book. Our book specifically states that a function is concave up when the second derivative is greater than 0, greater than 0. Well, if we look back at our second derivative equals 0 at pi. So we have to be sure that we do not write this as pi over 3 to 5 pi over 3, because that would include pi, and we are not concave up at pi. Now, we do have inflection points. F has 2 inflection points, right? 2 inflection points. What are those inflection points? Those inflection points are concave down to concave up. A change in concavity is an inflection point. So one of those is pi over 3, and the other inflection points, concave up to concave down, 5 pi over 3. So at this point, we've answered part A, we've answered part B, we've answered part C, which were to find where this is increasing, find where it's decreasing. We've done that. Find local mins and local maxes. We've accomplished that. Tell us where the function is concave up and concave down. We've accomplished that. And tell me where we have inflection points. We've done that as well. Now, let's put an and in there. So what was the last thing they asked us to do in problem 31? Well, in problem 31, they said use this information to sketch a graph of our curve. Now, I'm going to do the graph right over here. Okay, so now remember, we're restricted to the domain from 0 to 2 pi, right? 0 to 2 pi. So we'll call this 2 pi right here. Now, I like to begin by plotting some points. And the points that I'm going to choose to plot are going to be the endpoints of my domain, the beginning and ending of my graph. I'm going to plot my minimum, right? And I'm going to plot my inflection points. So all of those points need to be plotted. So before we can begin, we have to find f of 0. I'm just going to do these. Well, you know, we can write these down over here if you want. Maybe you want to see the work. So f of 0 is going to be what? That's going to be 2 times cosine of 0 plus cosine of 0 squared. All right? So what do we get for that? Cosine of 0 is 1 times 2 is 2. Cosine of 0 is 1 squared is 1, so that's going to be 3. Now, f of 0 is going to be the same as f of 2 pi. So on our graph, those points are going to be, we'll just go 1, 2, 3. We're going to have 3 here, and over here we're going to have 3. Okay. So this is the point 2 pi, 3, and this point here is 0, 3. Okay, those are two important points on our graph. Now we know we have a local minimum at pi, and our local minimum is -1. So at pi, we have a local min right here of -1. So this is pi, -1, and we know that's our local minimum. That's the smallest point in that interval. Now, what else do we need to plot? Right? We'll change colors. We've got this. We need to plot our inflection points, right? That's what we need to plot. We need to find f of pi over 3, right? F of pi over 3. So we'll come back over here. What's f of pi over 3? Well, that's going to be 2 cosine pi over 3 plus cosine squared of pi over 3, right? And so what does that give us? Well, let's find cosine of pi over 3 first. Cosine of pi over 3 is 1/2, right? It's adjacent over hypotenuse, cosine adjacent over hypotenuse. So cosine of pi over 3 is 1/2. So that's going to be 2 times 1/2, that's going to be 1. Right? That's going to be 1. And then what do we have here? We have cosine squared of pi over 3. Well, we just said cosine of pi over 3 is 1/2, right? 1/2. So we're going to square that. That's going to be plus 1/4, and we're going to get 5/4, right? So at pi over 3, at a third, right, a third of the way between 0 and pi, at pi over 3 here, at pi over 3, we have an inflection point at 5/4. So we're going to go ahead and put that in green, right? That is pi over 3, comma, 5/4. Okay. Now, what about f of 5 pi over 3? Well, if we do a little analysis before we do some calculations, 5 pi over 3 is in the 4th quadrant. Pi over 3 was in the 1st quadrant. Cosine is positive in both 1st and 4th quadrants. The reference angle for 5 pi over 3 is also pi over 3. So in other words, what I'm trying to get at here is that the value of f of 5 pi over 3 is going to equal the value of f of pi over 3. So we're going to get 5 over 4 is there as well. So where's 5 pi over 3? Well, 5 pi over 3 is a third of the way from here, right? So we'll put that here. So we'll put our inflection point right there. So that's going to be our second inflection point. Now remember, that point is 5 pi over 3, comma, 5 over 4. Okay. All right, so what's left to do? Well, what I like to do at this point, what I think makes drawing the graph a little simpler, is I like to draw below my graph a line. This line has nothing to do with the graph. On this line, I'm going to label where my function is increasing and where my function is decreasing. In other words, I'm going to come over here to pi, I'm going to put a mark, and I'm going to say, well, what do I know between 0 and pi? I'm going to write decreasing right here, okay, decreasing. Between pi and 2 pi, I'm going to write increasing, okay? And then I'm going to draw another line, and this line, I'm going to use this line for my concave down and concave up. My inflection point is here, right? This is one inflection point. This, remember, pi is not an inflection point, but it is a place where I could have to discuss concavity. And then I have 5 pi over 3 here. Now, what do I know? I know right here I'm concave down, right? Right here we're concave down. Also, we're concave down here, so I'm going to put a CD over here for concave down. Now, what about concave up? Well, we're concave up on this interval and concave up on this interval. Now, what is the purpose of these red lines? Well, the red lines are there to guide me as I draw my graph. I know that as I start my graph here, I'm decreasing and I'm concave down. So my graph's going to come down, it's going to be concave down. But at this inflection point, right, at this inflection point, I know that I'm going to switch to being concave up. I'm still going to be decreasing, but I'm going to be concave up all the way down to there. Now I'm increasing but concave up as I go this way. And at this point, I switch to concave down. And we've got our graph. Now, if we wanted to be more exact, we could find the zeros, right? We could factor this, and we could find the zeros. We could find these 2 points. They didn't ask us to do that. I'm not saying we would have to do that. I'm just saying it's an option, all right? So that's a complete solution of problem 31. Right? So I'm going to do one more of these. I'll go ahead and erase this. There we go. So, in addition to problem 31, right, it looking at the homework assignment here, like we stop at 33 and 37. So, I'll go ahead and work on problem 33. What's different about problem 33? Well, I know some of you don't like fractions, and problem 33, problem 33 comes with a fraction. So what are we looking at here? We have f of x, right? F of x equals x squared divided by x squared minus 1. Okay? And the question we're asking to answer here is exactly the same. It's got one added part, and we'll do that part first. But other than that, it's increasing and decreasing. Where am I concave down? Where am I concave up? Do I have any inflection points? Can you draw me a sketch of the curve? Okay, that's what they want us to do in problem 33. So where do we begin? Well, we begin by finding the derivatives. Okay, so what are we going to do? Well, we're going to have to use the quotient rule here. So f prime of x is going to equal, remember, to do the quotient rule, we want the denominator squared. Okay? We begin with the denominator here. We multiply by the derivative of the numerator. That's going to be 2x minus the numerator, which is x squared, times the derivative of the denominator, which is going to be 2x again. Now, if we factor this, right, if we factor this out, what do we get? Well, we can take a 2x out of both of these, and we get 2x times, here we have x squared minus 1. Here we have minus x squared, right? So that worked out very nice. And on the bottom, we have x squared minus 1 squared, right? X squared minus 1 squared. So, if we simplify this, right, if we simplify this, what do we get? We get, on the top, we get minus 2x, right, minus 2x, times, and on the bottom we have x squared minus 1 squared, right? X squared minus 1 squared. So if we go back through this real quick, just to make sure we didn't make any mistakes, you don't want to mess up the first derivative in one of these problems. If you mess up the first derivative, everything after that is going to be gone. So we decided we were doing the quotient rule. We wrote the denominator squared. Then we wrote the denominator here. We took the derivative of the numerator and we said that was 2x minus. The numerator is x squared. The derivative of the denominator is also 2x. I factored a 2x out of both of these, put it here. That left me x squared minus 1 in this term, minus over here, I was left with just an x squared. X squared minus x squared is 0, so I have a negative 1 times 2x, and that's my first derivative. Okay. Now, where do we go from here? Well, we're going to find the second derivative. So we might as well get that out of the way right now. Again, we're going to need the quotient rule. So we'll do our bar, our fraction bar. We're going to have x squared minus 1, right? But now we have it squared, and we're going to square it again, so that's going to be the fourth power. The numerator is going to be x squared minus 1 squared times the derivative of the numerator, which is just minus 2, right? Just minus 2, minus the numerator itself, which is minus 2x, right? So we got to get both those negatives in there, times the derivative of the denominator, which is going to be 2, times x squared minus 1, right? That's the power rule. We got to do the chain rule. That's going to get multiplied by 2x. So let's see what this all works out to be when we get done. What can we factor out? Well, we have a negative 2, and here's a negative 2, so we can take out a negative 2 if we want. Here's an x squared minus 1 squared. Here's an x squared minus 1. We can bring an x squared minus 1 out. So let's do that. Let's take out the x squared minus 1. Okay. That's to the first power, so that we can take out. Let's go ahead and bring out a negative 2. Let's bring out a negative 2. And let's see what we have left. Here, we're going to have the negative 2 is gone. We factored it out. Here, we're going to have x squared minus 1 to the first power. Now, be careful. We factored out the negative 2. We did not factor out this negative. So we're going to have minus here. And then we're going to have what? We took the negative 2 out. So we're going to have x, we're going to have 2, and we're going to have 2x. So we took out the 2, we have the x left, right? The 2 is gone. We have the x and the 2 and the 2 and the x. So that's going to be 4x squared, right? 4x squared. Now our denominator is going to be x squared minus 1 cubed. Okay, so where do we go from here? Let's see what we have. Well, this x squared minus 1 will cancel. I've already, I guess in my head, I'd already done that, hadn't I? Because this is going to be a 4 down here, but then we're going to cancel. We're going to make that a 3, aren't we? That's where my brain was ahead of my pen. Now, what do we have inside, right? We have a negative 2 now, right? And inside our brackets up here, we have negative 4x squared plus x squared. That's minus 3x squared. We have a minus 1. On the bottom, we have x squared minus 1 cubed, right? So what does that equal? Well, we've got a lot of negatives. Those negatives all go away. And so we have 2 times 3x squared plus 1 all over x squared minus 1 cubed. All right? So what am I going to do at this point? Well, apparently I should feed my cat, since I'm sure you can hear it meowing in the background. So where do we go from here? I'm going to jot these derivatives down up here. Okay, I'm going to put them down right up here so we can get them out of the way. We can use them later. F prime of x, we decided, was negative 2x divided by x squared minus 1 squared, and f double prime of x, right? What did we say f double prime of x was? We said it was 2 times 3x squared plus 1 divided by x squared minus 1 cubed. All right? So those are our derivatives, so I'm just going to clean this off here. Get this out of the way. All right. So there was a different beginning to this problem, right? This problem begins with a request that we find any horizontal and vertical asymptotes. So this is going to take us back to a little pre-calc, right? So vertical asymptote. What do we know about vertical asymptotes? Well, this is a rational function. We don't have to work very hard to find the vertical asymptotes of rational functions. We don't have to break out any calculus here and start looking for things involving limits when we're asked to find vertical asymptotes of rational functions. Vertical asymptotes, because this is a rational function, we're looking for where does the denominator equal 0. Well, our denominator is x squared minus 1. That's x plus 1 times x minus 1. And when does that equal 0? That equals 0 at x equals plus or minus 1. So we have vertical asymptotes at x equals plus or minus 1. They also want us to find horizontal asymptotes, right? Horizontal asymptotes. Well, again, we don't have to break out any calculus here. We know how to find horizontal asymptotes with calculus. We take the limit as x goes to infinity. We take the limit as x goes to negative infinity. But we had rules in pre-calc that said if you have a rational function and the degree of the numerator is equal to the degree of the denominator, the ratio of the leading coefficients is your horizontal asymptote. So our horizontal asymptote here, based on the ratio of leading coefficients, our horizontal asymptote is y equals 1 divided by 1, or y equals 1. So right now, we have horizontal asymptotes and vertical asymptotes for this function. And they asked us to find those, right? They asked us to find those. That's part A of this question. So part B says, where are we increasing and where are we decreasing? Now, we know we know what to do. We're going to find the critical numbers of f prime of x. All right? Now, what do we do to find the critical numbers of f prime of x? We check to see where the derivative equals 0. Right? That's always our first step. Our derivative, if we took a look up here, our derivative is a fraction, right? We have minus 2x in the numerator. We have x squared minus 1 squared in the denominator. When is a fraction equal to 0? A fraction is equal to 0 when the numerator is equal to 0. So this results in us setting negative 2x equal to 0. We solve that. We get our first critical number, x equals 0. Now, in our previous problem, we didn't have to worry about when does the derivative fail to exist. In fact, if I was grading my own work in the previous example, I would probably take off points because I don't remember me actually adding this to my problem-solving strategy. We want to always include this. When does the derivative fail to exist? Even if the answer is never, we want to include this because the teacher is going to assume if we don't include it, we forgot it, kind of like I did on the last example. And they're going to take off points for that because they don't know if we left it out because the answer was never applies, there is no place where the derivative fails to exist, in other words, or did we just forget to do it, like Kevin did in the last example. So in this problem, however, there is going to be an answer to this. We have a denominator. This denominator is x squared minus 1 squared. Well, x squared minus 1 squared equals 0 when x squared minus 1 equals 0. And we know when x squared minus 1 equals 0. We did that analysis right up here. That gives us two more critical numbers. X equals plus or minus 1. Okay. Now, question. Are these values in the domain of this function? They're correct. They're not in the domain of the function. However, that doesn't mean that they're not going to be places where the function can change from increasing to decreasing. We're going to have to still consider those points, right? We're going to have to consider those points when we run our sign test, which is what we're going to do next. So next we'll do the sign test, right? So what do we do for the sign test? Well, we put down, right? We put down our critical numbers. We have 0, right? We have 0. Well, I guess we'll put 0 here, won't we? We have positive 1, and we have negative 1. What are our factors? Well, we have a negative 2, we have an x, and we have x squared plus 1 quantity squared. Don't forget that it's x squared plus 1 quantity squared. Why is that important? Well, when we square somebody, all of our results are going to be positive, right? And positive squared is positive, negative squared is positive. What about x? Well, if we pick a number smaller than 0, it's going to be negative. If we pick a number bigger than 0, x is going to be positive. Negative 2 is going to be negative everywhere. We got to remember to include that. We don't want to leave that out. And what do we come to? What do we get here? We get positive here. We get positive here. We get negative here, and we get negative here. Right? Now, be careful. Be very careful. It didn't happen in this problem as being a possible outcome. This is increasing. It's still increasing. We would not have said this is a local min or a local max, because increasing to increasing, that is not a local min, that is not a local max. But whenever I run a sign test and I have numbers on my number line that are not in the domain, I like to do something on my sign test, like put an open circle around them, to let me know, hey, this is not going to be a local min or a local max, because that number is not in the function. If it's not in the function, it can't be a min or a max of the function. It's not in the domain of the function. So what are we going to conclude here? We're going to conclude, right, f is increasing on, right, where negative infinity, right, negative infinity to negative 1, union negative 1 to 0, right? That's where f is increasing. F is decreasing on 0 to 1, union 1 to infinity. Do we have any local mins or local maxes? Well, right here, we have zeros in the domain, right? If I put 0 here, I get 0 divided by negative 1. That's in the domain. The function is increasing, and now it's decreasing. So 0 is the location, right? 0 is the location of a local maximum. F has a local max at x equals 0. The local max is f of 0. And f of 0 is 0 divided by negative 1, which is 0. All right? So the question said, find vertical asymptotes. Check. Find the horizontal asymptotes. Check. Tell me where the function is increasing. Check. Tell me where the function is decreasing. Check. Tell me if it has a local max or a local min. Check. So we've got those parts done. What's left? Well, concavity, right? Concavity and inflection points. And we know where we're going to go. We're going to find the critical numbers of f double prime of x. And we know how to do this. We're going to duplicate the work that was done over here. We're going to start by saying, well, when does f double prime of x equal 0? F double prime is a fraction. Fractions equal 0 when the numerators are equal to 0. Well, if we take a look at our numerator, 2 can't be a 0. 2 is a constant. And even if we tried, right, if we wrote this down, we didn't realize it before we started, 3x squared plus 1 cannot be 0. If you move the 1 over, you get 3x squared equals negative 1. You divide, you get x squared equals negative 1/3. When you square a number, you're not going to get a negative. Square is always positive. So this has no solutions, right? No solutions. What does that mean? Well, that means we don't get any critical numbers for that case. What about, however, f double prime of x fails to exist? Well, here we know when this is going to fail to exist. It's going to fail to exist when x squared minus 1 cubed equals 0. Well, we've played this game. This happens when x squared minus 1 equals 0, and we know that gives us x equals plus or minus 1. So we do have 2 points for our sign test, so we're going to have to run our sign test. On some problems, you end up with no points for your sign test, and then you just run the sign test. You don't have any intervals. You just pick one test point, and the function is always concave up, or the function is always concave down. Kind of like e to the x, right? When you think about the graph of e to the x, be it boring as it might be, is always concave up. So, sign test. Well, where do we go? We have our critical numbers. We plot those, right? We put -1 here, put +1 here. We got to write all our factors down. Now, our factors are 2, 3x squared plus 1, and x squared minus 1 cubed. Right? 2 is always positive, so that's going to be plus, plus, and plus. We decided 3x squared plus 1. I mean, that's always positive. What about x squared minus 1 cubed? Well, we can pick test points. If we put a 0 in here, we get 0, right? 0's here, right? So if I put 0 in here, I get 0 squared, which is 0, minus 1, -1 cubed. That's going to be negative. What am I going to pick down here? Down here, I'm going to pick 12 billion, but it's negative 12 billion. But when you square negative 12 billion, you get a positive. Take away 1, still positive. Cube it, still positive. What about over here? Well, we can pick 10, right? I thought yeah, I know, you thought I was going to pick positive 12 billion, but we'll pick 10. 10 squared is 100. 100 minus 1 is 99. 99 cubed. Now what do we get here? We get plus, we get minus, and we get plus. Now don't forget, the reason we do this sign test is this right here, right? This is the sign of the derivative. This is the sign of the second derivative. And so we can write our conclusions down, can't we? We can say f is concave down on -1 to 1. F is concave up on -infinity to -1 union 1 to positive infinity. And now we have to be very careful, right? What about inflection points? Well, I see what you see. Concave up, concave down. That is definitely a change in concavity. Concave down, concave up. Also a definite change in concavity. But, these 2 points are not in the domain of our function. So when it comes to inflection points, we have none. We have none. Now, the final thing that they'd like us to do here is to draw the graph. They'd like us to draw a graph of this function. So if we come over here, what do we know? Well, we started all the way back here with vertical asymptotes. We said, well, we have a vertical asymptote at 1 and -1. And we said we have a horizontal asymptote at +1. Okay. Now, what other points have we found that have any significance on our graph? Well, we did find out that f has a local max at 0, 0, right? There's a local max right here at 0, 0. This is a local max. Now, again, I personally like to draw my bars down here like this, and I like to label my bars. Now, I know from -infinity to -1, -infinity to -1. That's this bar right here. F is increasing. Right? So right here on my table. F is also increasing from -1 to 0. -1 to 0. Right here, F is also increasing. All right? But F is decreasing from 0 to 1. So right here, F is decreasing. Right? F is decreasing. And then on the other side, f is decreasing from 1 to infinity. F is decreasing. Right? So we have this when it comes to increasing and decreasing. Then what about for our concavity? Well, we're concave up, right? We're concave up from negative infinity to negative 1. That's here. Concave up to negative infinity to negative 1. Now we're concave up also from 1 to infinity, right? We're concave up over here. And then we're concave down, right? We're concave down across this interval right here. Concave down. So what does our graph look like? How are we going to draw our graph? We don't have very many points. We have one dot. Now, what would you do? I think a good idea would be to put in some more points. Let's plug in negative 2 and see what happens, right? Let's just do some scratch work. What's f of negative 2? Well, f of negative 2 is negative 2 squared, right? Divided by negative 2 squared minus 1. That's going to be 4, right? Negative 2 squared is going to be 4. 4 minus 1 is going to be 3. Correct. 4/3. What's f of 2? Well, this function's even, if we remember that. So f of 2 is going to be the same as f of negative 2. We're going to get 4/3. So at 2, right, at 2, we're right here at 4/3. And here we're at 4/3. Now we know these are vertical asymptotes, right? We know they're vertical asymptotes. What does that mean to us? Well, we know our graph goes through this point, and we know our graph goes through this point. So, graphs can cross horizontal asymptotes. Don't think that just because the dot's there, we can't get down here. But we can see what's happening right here. Our graph in this region right here, we need a graph that's decreasing. Decreasing. This is a vertical asymptote. Our function either goes up there or it goes down here. Those are the only two choices. If I were to leave this dot and travel this direction, that function would not be decreasing. As I move to the right, that function would be going up. That means the only choice I have is to have a function that goes like this. Now, this function has to be concave up the entire way, so this function goes like this. Right? Over here, by exactly the same argument, and because the function itself is even, which means we have symmetry across the y-axis, we can see that over here, our graph goes like this, right? I guess it's technically supposed to go through my dot, isn't it? So we'll make it look like this. Now, what's going on here? Well, on this side, the function is increasing. On this side, the function is decreasing. So I start here, my function is decreasing. This is vertical asymptote, so it's going to get closer and closer to that. I do have symmetry. But over here, it's increasing. This is a vertical asymptote. It has to be concave down, so it looks like this. So this is the graph that goes with problem number 33. All right. I hope this gets you some inspiration, provides some inspiration, and gets you going with your homework. I'm going to put together another video where I'll do homework problems from section 4.4 as well. So I hope this finds everyone well, and enjoy your increasing and decreasing and your sign tests. If you lay it out like this, and you keep it laid out like this, then when you get to the actual graph, all your information is presentable, it's organized, and it's easily interpretable by both you and the person that's grading your work. And for a lot of you, that's me. So if you think that was a hint, good job, because that was a hint.